So let's start with the overall presentation of the board. I designed this board to be drop-in replacement for Arduino Nano, so all the pins are in the same order of Arduino Nano. And we have the digital pins, we have the analog pins. I also listed the STM32 pin names, because you can use this board not only with Arduino, but for instance you can use it with STM32 ecosystem, you can use STM32 hardware abstraction layer and so on, so you are not tied to Arduino. In terms of voltage, so this is a 3.3 volt logic level board. In addition to that, an advantage is the fact that for most of the current sensors you are not gonna need level shifters anymore. So it works at 3.3 volts. And moreover, most of the pins are also 5 volt tolerant, which means they accept 5 volt inputs when used as digital inputs. There are 3 exceptions. D2, A1 and A3 are not 5 volt tolerant. The rest of the pins are 5 volt tolerant in digital mode. For the analog pins, they are placed in the same position like on Arduino Nano. There is an exception, so we don't have analog functions on A4 and A5. They still retain the digital functions and the I2C functions, but not the analog functions. Don't try to use analog read on A4 and A5 because it's gonna crash, and this is a limitation of the Arduino framework, the way it is written. To compensate for the lack of 2 analog channels, I mapped 2 more, A8 and A9, so you can refer these in your analog read functions and you can use these pins. In analog mode, when you use a certain pin in analog mode, you need to be careful. The voltage should not exceed 3.6 volts. The PWM channels are also in the same placement like on Arduino Nano. We have the pins 3, 5, 6, 9, 10, 11. In addition, we have 2 more. We have on pin 12 and on pin 21. I also wrote here in these labels the timers and the channels to which these pins are connected, if you want to work with them low level or using the STM32 ecosystem. The rest of the peripherals, the serial, SPI, I2C, they are in the same place on the same pin locations like for Arduino Nano. Also the LED is on D13. If we want to use the analog reference, external analog reference for ADC, by default the chip's ADC reference is connected to 3V3 pin, and we have this jumper here, and it's this part connected here. So if you want to use an external analog reference, you need to cut this part of the jumper and put here a solder jumper to connect to this ARF pin. What else do we have here? We have at the top of the board, we have the debugging header, where you can connect an ST-Link to program and debug the board. We have here a power path selector. I will discuss more in a later section of the video how the board can be powered and how you can choose between 2 options. On the board we have 2 buttons. We have here a boot button, which is used to be able to transfer the software into the chip, and at the top of the board we have the reset button. So that was in a nutshell the overall presentation. So consider it as a drop-in replacement for Arduino Nano with very few exceptions. Now let's discuss about software installation. We start by installing Visual Studio Code. Next. It's gonna take a bit to install. Good. Now we have Visual Studio, we go to extensions, search for Platform IO, install Platform IO. Okay, we reload. Now we go to GitHub and search for Green Pill Nano. We find the repository for Green Pill Nano skeleton. We download the zip. We move it to the projects folder. We extract it here. Now we go to Visual Studio Code, pick folder, we select this, and please be careful because it creates two embedded directories, one within each other. Choose the innermost one. Now, because there was no previously installed STM32 platform, is going to install it and it's going to take a while. On my laptop it took about 12 minutes, so be patient. Now we can compile, and we have a successful compilation. Let's connect the board. First we start with the power jumper, we put it in the USB position, then we connect the board to the computer. We press the boot button and hold it, then we click on the reset button and release it. Afterwards we release the boot mode button, and now the board is in boot. We can upload the code. Being the first time, is going to install some additional tools for flashing the chip. And it failed. It failed because we don't have a driver associated with the STM32 bootloader. So let's install it. We go to Google, search for Zadig, download Zadig. We start it. We click on list all devices. We select the STM32 bootloader, select WinUSB and install driver. It's gonna take a couple of minutes. We are done. Let's try again to upload. And now it seems like it's working. And it's working. We have the LED blinking. We can also upload the code using ST-Link V2 or V3. In order to do that, we need to copy the Green Pill configuration file to the OpenOCD directory. On your computer, this is the path. You just replace AC with your Windows username. We connect the ST-Link, and we also install using Zadig the ST-Link driver in the Platform IO INI. We have to uncomment these two lines. We click upload, the LED flashes and the code is downloaded. While I don't recommend clones, if you happen to have one, you comment out those two lines for official ST-Link and uncomment the lines for the clone. We hit upload, and the code is running. If you use the clone, connect only 3 pins, connect the clock, the IO and the ground. The board has a power path selector implemented with the jumper and the pin header, so let's see why we need this. The board can be powered, and the main power line, this 3v3 net, which is also connected to the 3v3 pin, can be powered in two ways. One way is with the voltage coming from the USB bus. The voltage is regulated using an LDO, and it outputs 3.3 volts. The other possible power path is with the voltage coming from V-in pin on the board. You can see that on the V-in pin there is no voltage regulation. This MOSFET here is used as reverse battery polarity protection. So if you happen to put the batteries in the wrong orientation, it will not fry the board. The way you select which power source is used for the board is by placing the jumper. If you place it in this position here, it will use the voltage coming from the USB bus. If you put the jumper in this position, it will use the voltage coming from VIN. The board was designed to be ultra low power, so that's why when using the VIN there is no voltage regulation. Voltage regulation would have implied voltage regulator, which means a voltage drop on it, which means less battery availability. Also, it would imply a quiescent current. So in order to have the minimum possible waste, actually zero waste, we don't have any regulation on this. So the board was designed to work with 3-volt batteries. For instance, CR2032, it could work with 2 AA batteries, 2 AAA batteries, or if you want a very long life battery, you can choose the CR123. So be careful, don't apply a voltage higher than 3.6 volts to the VIN pin. Don't use a lithium polymer battery, because those rechargeable batteries, if fully charged, definitely exceed 3.6 volts. They can go up to 4.2 volts and it will fry the board. If you want to use a rechargeable lithium polymer, add a voltage regulator before you connect it to the VIN pin. Now we have the setup done. Follow for the low power tutorial and the debugging tutorial.